Okay. First, thank organizers for inviting me to this beautiful workshop, and also the beautiful castle for this workshop. So I heard a lot of interesting talks. So some of them really relate to material, and for instance, long temperature quantum spin Hall effort, and also a lot of interesting theoretical talk. So my talk will be on quantum spin Hall insulator made by semiconductor. So this semiconductor is called the indium arsenide gallium indium antimony. So so this is the effort try to make to improve the material to make the energy gap, bulk gap become larger. Of course, not as large as the room temperature, but is much larger compared to the previous material, indium arsenide gallium antimony, by our order of magnitude. So first, because this is a short talk, so I just talk two parts. First, what is strainer layer indium arsenide gallium antimony? And second is what's the property of those materials. So the motivation, of course, there are many interesting things to do with a 2D topological insulator. One of the motivation is to replace the 1D wire for realizing the Mariana boundary state. The advantage here is theoretically that this is a single mode, already spin polarized, and basically you don't need a magnetic field to generate the Zeeman splitting. And number 4 is this material itself is two-dimensional, but the active part, which is a one-dimensional, is controlled by gating in two-dimensional case. So if we look at this view of the Mariana 1D state, edge states, there are two different platforms. One is 1D wide, so you use those parameters, the Fermi energy or chemical potential and the energy gap of the superconductor, then also the Zeeman energy. You can turn these in the 1D case to turn to the topological case, or P-wave one-dimensional wire. So you need a finite strength of the magnetic field applied to the system. Now, if you don't apply magnetic field, you end up the trivial state. But on the other hand, for two-dimensional topological insulator, if you work on the edge state, then this phase diagram actually opposite to this. So you work on the zero magnetic field. You don't apply too much magnetic field, or else you will get into travel range. Okay, so that's a really complement with each other. So the device is designed is you have a 2D topological insulator, you have edge state going around. Then you want to cut this edge state by gap out the edge state. One way to do is to put a ferromagnetic insulator on these 2 points. Therefore, a pair of Mariana boundary state can be localized here. Okay, so basically from this cartoon, that you can see that we need an edge state. Then you need a proximity effect. Also, the proximity effect from the ferro insulating ferromagnetic. So you need 3 ingredients. So basically, I'm here want to emphasize how do we make edge state which are suitable for those kind of device. So the material is a well-known semiconductor. So this is called a 6.1 Armstrong family. So notably here is a indium arsenide, which has an energy gap 0.15. Let me see. You have energy gap 0.78 EV, and then next to it you have a gallium antimony, which is the energy gap here. Then you have the valence band Borden is above the conduction band of the indium arsenide. If you group together, then you have an inverted structure, showing here the the ground state of the conduction band is lower than the ground state of the valence band. So if you allow these to be a tunnel with each other, then you have a hybridization induced energy gap at some finite k or the kf point, kf and a minus kf. So you open a small gap. This small gap is called a mini gap on the order of 4 to 5 milli-eV in the usual parameter range. And then a pair of Kramer's pair will generate and will propagate along the edge, along the perimeter of the sample, and then this will be spin momentum locked. So if you look at the parameter for those material, you can change this inversion from all the way to inverted to non-inverted by changing the thickness of the material or by gating. And then if you are in the inverted range, you have 150 milli-eV range to be turned. So you can not only change the level of inversion, you can also change it from inverted to non-inverted in principle by gating. Okay. So this is a material being widely used in industry, the infrared detectors together along with mercury telluride. There's two types of material which are used for those detectors. Mercury telluride actually is the first material showing the quantum spin Hall effect. And that's the indium arsenide gallium antimony is the second material showing the quantum spin Hall effect. So, so the device looks like this. Schematically, you have 2 layers grown by MB indium arsenide, for instance, 15 nanometer, and then gallium antimony is 8 nanometer. So you make this double layer structure. The rest of these just a supporting structure like substrate and also the cap layer and some dopings, etc. So now if you have one substrate which is a doped substrate can be used as a backgate, and you put aluminum or other material is a top gate. So you have a double gate device to control what is the density of electron and holes. And you can contact these to outside by superconducting leads or by normal leads. So here's the phase diagram. So this phase diagram really is plot in terms of the front gate voltage and the back gate voltage. So you can turn this system into a charge neutral point. Here is a line. Along this line, basically, the electron density will be equal to the hole density. Therefore, the whole system is charge neutral. So along this charge neutral point, you have some range of the parameter. You can see the topological insulator. So in detail, we can divide this phase diagram into 3 different regions in terms of the density. So the first region is so-called deeply inverted region. Basically, you have high density of electron holes. Although they are equal in number, the system is not really insulating, rather it's semi-metal because the energy gap pretty small as compared to the other parameter. Therefore, you basically have poor metal or semi-metal like this. Now, if you go to the opposite, the other side of the phase diagram showing here is that basically you have normal insulator or semiconductor, usual semiconductor. Therefore, this travel regime. What is interesting is the regime between this semi-metal and the semiconductor. You have some region that the density is low enough. How low is low? In this case, 1 × 10⁻11. That's the typical number we have. Now, if the density is much higher than this, you never get energy gap. Actually, you always see semi-metal behavior. So you have to push this into relatively low density, 1 × 10⁻11. then if you can use the gate, you can push down to this point. This point is the critical point between the inverted and non-inverted. So sometimes we call it the touching point, which means these two bands, the band edge will couple to each other. Now, if we disregard the interaction, we will think this is the region for topological insulator and this is the region for the semiconductor. But if we take into account the interaction, this critical point or the region around the critical point actually very interesting because the attraction between the electron will lower the total energy, therefore form a stable or spontaneous exciton state. Under a very strict condition, it became exciton condensate or exciton insulator. So for today's talk, we basically want to talk about low density, but not as low as getting into the exciton insulator region. So this is the region that we observe quantum spin Hall effect. So the signature for this, of course, is the quantized edge transport. In small devices, these devices typically have the size of 2 micron. Now, if your sample is less than 2 micron, you are able to see the quantized edge transport. Depends on how do you connect to the device. This is a 6-terminal device. It is a 4-terminal device, and according to the Butyk formula, you will get a different number of quantization. So this is a 4e squared divided by h. This is a 2e squared divided by h. And also one can make such as small devices, 1 micron, 1 micron. This is so-called H-bar device. Now, if you apply, if you pass current here and you measure voltage here, you can get a non-local transport. And non-local transport is supposed to give you a quarter of h divided by e squared of the resistance, which is 6.4 kilo ohm. So that's what one can observe. So this looks all fine. This looks like some kind of a proof for the quantum spin Hall effect. But if you make the sample bigger, much bigger than this typical size of 2 micron, then you end up non-quantized edge transport. So this edge actually became ohmic. So you have a 10 micron, 20 micron, 50 micron length, and the resistance actually proportional to the length. Now, what's the reason for this? We're going to mention later, but just from the experimental point of view, you have two regions. You have small sample, you see the quantized transport. If you go to the sample size larger than certain characteristic length, you end up to non-quantized edge transport. Okay. So what is this characteristic length? We define this as a 4 micron. The reason that we use this one is if you look at this plot, linear plot, you can find the ratio of this, which means for how many micron you will get 1 unit of the quantum resistance. Okay, so by 1 quantum unit, 1 quantum resistance, we define a typical length or characteristic length is 4 micron. So look like this long sample is a series of quantum resistance. Each one is 4 micron long. Okay, so what determines this 4 micron certainly has to do with the physics of the backscattering. Okay, so later we are going to dig into this. The other property for the same type of sample, which is made of indium arsenide, gallium antimony, typical energy gap is like 60 Kelvin. Okay, so this is about 4 to 5 millieV is calculated by the band structure calculation. So if you apply implant magnetic field up to here from 0 to 8 Tesla, what happens is that due to the tunneling between electron hole layer you're supposed to have momentum transfer perpendicular to the magnetic field. So if you calculate this, then this tunneling induced momentum transfer is going to make this energy gap tilted. So one side, the energy gap opens here, the other side opens on the other energy. Therefore, in the end, across the Fermi energy, you will not have energy gap. Rather, is like a semi-metal. Okay. So if according to this picture, if you apply high enough magnetic field, eventually you will turn this quantum spin Hall effect into semi-metal. Okay, so that's one of the criteria used in the reference paper to distinguish whether this is a topological insulator or regular semiconductor. Because if you have a regular semiconductor, you apply implant magnetic field, basically nothing will happen. Therefore, you can identify that is a semiconductor band structure. But showing here up to 8 Tesla, and also in other experiment we go to as high as 20 Tesla, we don't see anything change in terms of the conductivity. Therefore, in this material, we will see that there is no such consequence of coming from the implant magnetic field. Okay, so what might be the reason? One of the reasons is this picture is based on tunneling between electron and hole layers. If there's no tunneling, of course, this will not happen. Therefore, in the case of this, we guess there might be in the very low density region, the tunneling somehow is suppressed, and therefore this single particle picture hybridization gap does not occur. Okay. Of course, one of the scenario is this tunneling in such a low density is overwhelmed by the electron attraction between the electron holes. Therefore, these electron hole form pairs. They are fixed in the each quantum wells. So that gives some scenario of exciton insulator. And then later we do measure the optical absorption in those in this region, and you can find the signature of the exciton formation, and also you can find the predicted energy gap related to the exciton condensate. So so from this we can see that even this can be treated as a single particle picture of the hybridization induced gap, and you can understand this by looking into the band structure, etc. But in reality, in such a low density, there might be strong influence from electron hole interactions or even the exciton insulators. Now, if we apply magnetic field, what happens for the edge state? And then we can measure those in different type of samples. One can find this edge state conductance showing here is the conductance of the edge state pretty much remain the same for different size of samples. So this is from 0 all the way to 12 Tesla, and the conductivity basically remain flat for all these samples or for different lengths. Now, if you apply a perpendicular magnetic field, one can find for some sample the conductivity goes up. For some sample, conductivity goes down. So how do we understand this? Simply because if you have Hall bar geometry, then basically for two-terminal measurement, you end up measure the Hall resistance itself. So what you measure actually the Hall resistance caused by perpendicular magnetic field. Now what happens for these three? These three look like all the effect is to cause the conductivity to going up under perpendicular magnetic field. So that's maybe related to the formation of the chiral state instead of the helical state. Because under perpendicular magnetic field, you break time reversal symmetry. So the magnetic field will favor one branch, disfavor the other branch. Therefore, they are not completely cancelled with each other. Okay. So, so if I summarize this first generation of sample, the indium arsenide gallium antimony, this has some properties: quantized conduction for small samples, non-quantized conduction for larger samples. Conduction does not change under high parallel magnetic field. Okay. So now we examine what is maybe the physics related to this. Is first we notice the velocity of the edge modes is extremely small. So here one can estimate what's the velocity end up to 10 to the 10⁴ meter per second. And of course, if we compare this to semiconductor 10 to the 6 should be 10 to the 6 meter per second. So also the mercury telluride is also 5 10 to the 6 meter per second. So our system actually in the region is particularly with low velocity of edge modes. Now, if the edge modes has a very low velocity, it means the kinetic energy is relatively low as compared to the interaction energy. Therefore, we can characterize this as a strongly interacting one-dimensional edge state rather than non-interacting edge state in this particular type of devices. Okay. Now, of course, one can look at in the interacting case, one can look at what's the mechanism for backscattering. Early on, there are proposals looking for correlated two-particle scattering. This is under case that if there's a strong interaction in the edge state. So the spin is going to flip simultaneously pairwise. This is protected by the time reversal symmetry because it goes simultaneously. Once it goes like this, then the edge state will go like this. Okay, so edge state going to back like this. So this in effect opens a channel for backscattering. So the more interaction should be intuitively there should be more backscattering. So this backscattering causes this effective character length become shorter than ideal case. Ideal case, this should be very long, but now is a finite. This may be related to the pairwise backscattering. And then the other material-wise, this also can be related to spin axial asymmetry due to the spin orbital interaction. So ideally, this spin momentum lock is strictly independent of the k, but with considering of the spin orbital interaction, then this spin momentum locking actually is helical like this, axially dependent. So only when you have a k equal to 0, this spin and a spin down, spin up is opposite. And then goes to finite k, you can see this and this not necessarily have complete opposite direction. Okay, so that's cause additional channel for inelastic scattering. For instance, you have a finite temperature. If you have a phonon involved, then you can exchange the momentum and cause this pair to flip together. Okay, so also one can look at more deeper whether this is a interaction will be related to the helical Luttinger liquid proposed by this, especially by this group. So helical liquid with strong Coulomb interaction can show logarithmic temperature dependence, and also can become insulating at a very low temperature. So we did measure this edge state with those kind of behavior look like a power law. Okay, so one can get a power or alpha is a 0.37, and then you can translate to, you can calculate what's the Luttinger parameter, which is pretty small. It's a 0.23. Okay, so that's getting into strongly interacting region in this particular sample. So this was published 2 years ago. Now we want to do something completely move away from this. Whether we can reduce the interaction by changing the Fermi velocity. Okay, so one way to do is to emphasize the energy gap. If we make energy gap much bigger, of course the Fermi velocity is going to increase automatically, right? That's one of the things to look at. So this use the technique called string layer. So if we look at for this material, indium arsenide and the gallium antimony, they are basically lattice matched. This is about 6.05. They have very small lattice mismatch. Now, if we consider to put some indium, well, we can find that this lattice is going to mismatch. So if you grow this gallium indium arsenide on top of indium arsenide, you have lattice mismatch. You end up the epitaxial growth is going to compress this whole layer or a valence band layer. And as a result, band structure of the whole is going to change dramatically. Okay, so going here is a specific diagram showing how much change in terms of the energy. So from this, we can simply say under the compression strand, because of mismatch between these two quantum wells, the inversion of the band is going to dramatically enhance. So it became more inverted. Once more inverted, in order to bring back to the same alignment, the way is to reduce the thickness of those quantum wells. So initially, wider thickness, you basically can allow you to make a thinner quantum wells to bring back to the same alignment. And in this case, because this is thinner, therefore the wave function is much more strongly overlapped. Therefore, this helps to enhance the energy gap due to the hybridization. So the calculation shows indeed one can get this kind of effect in real samples. Of course, this technique is widely used for industry for making superlattice infrared detector. So we just borrow this technique in the case of a quantum spin Hall effect. Okay, so so this is a calculation done by another group in Japan. So this is the result for calculation. So for 20% indium, you induce about 1% strain in the whole layer. And then if you calculate by 8 band, you can find the energy gap is going to dramatically enhance if you go to like 2% of the strain. The energy gap is going to be about 408 Kelvin. Okay, so that's much bigger than previous one. So now we are going to just flash some of the results. First is indeed the energy gap. In this case, for 32%, we can measure is 250K instead of the previous 66K. Okay. Then other thing which relate to this, indeed the interaction of the edge between the edge now became weaker. Therefore, we can find the character length actually enhanced by more than 10 micron. So we can see that in this case, we can have character length as high as 11 micron. One can tune this by basically change the Fermi velocity by changing the density, and you can get a range of from 7 to 11, just in one sample. Okay, and one can find a quantized plateau in a sample which has a relatively long size, 10 micron. Okay, so the other property which is related to magnetic field dependence, I'm not going to detail, rather just to say now this sample really shows very sensitively depends on the magnetic field direction and the magnetic field strength. Therefore, this recover single particle picture of the Z2 topological insulator. Okay, so because my time is limited, so I just show last one transparent. So that's the summary. Basically, we say we can realize large gap topological insulator and has a proper edge state properties which is suitable for making the Marijuana platform. Okay, then future work will be focused on the on using those edge state. Lastly, I should mention this actually because this material is industry related. In industry, people already develop those CMOS technology based on exactly the same material, indium arsenide, indium gallium antimony, and to make a CMOS, and they can use those structure indium gallium antimony, indium arsenide to make a circuit, integrated circuits. So our plan is to use the same technique to develop a topological insulator or Marijuana circuit based on those techniques. So one of the result is so lastly, I should acknowledge my students and my collaborators. Thank you for your attention.